So let's find the maximum volume of this box then. So remember, we've got this function that describes the volume of the box. So after this point here, the maximum value, the value for x when you get a maximum volume. And we can see what it is. The maximum volume is roughly, if that's 200 and that's 300, about 260 odd. And x is going to be roughly 2.5, something like that. So when we go through the calculus and calculate the value of this x to give us a maximum, that's what we should be getting. So let's see, okay? Now, when you come to using the rules of algebra, the first thing is that each part of this needs to be differentiated separately. And before we do that, we expand out these brackets. So we get all the separate parts and then we differentiate them. So if you're going to have to differentiate something, the first step to do is to multiply out the brackets. So what I'm going to do is take the first one and then multiply out the second bracket with the x. So I'm going to just multiply every term inside this one by x. Multiply out that bracket. So I'm going to get 12x minus 2x squared. And now I've got to multiply out these two brackets. And algebraically, you remember, every term inside this bracket has got to be multiplied by every term in that bracket. So 20 has got to be multiplied by 12x, and then 20 times minus 2x squared, and then minus 2x times 12x, and minus 2x times minus 2x squared. I've got to be careful about the minus signs. Minus times a minus, plus, so be wary of that. So I'll end up with v equals 20 times 12x is 240x. 20 times minus 2x squared is minus 40x squared. Minus 2x times 12x is minus 24x squared. Minus 2x times minus 2x squared is plus 4x cubed. So, and that brings us to here, Cameron, because now I look at this and I add like terms. I can see that actually the x squared and x squared, now I can add them. So that tells me that the volume can be written as 240x minus 40x squared minus another 24x squared is minus 64x squared plus 4x cubed. Now, at this point, I have a function that I can differentiate. And we're going to go through all these conventions around differentiation and the rules after this. But for now, I'm just going to do it and show you just how easy it is. I can write down the differential. First of all, the convention for the differential function is dv by dx. That's how you'd say it, dv by dx. And it means the differential of v with respect to x. Differential of the volume with respect to the variable x. And that equals 240 minus 128x plus 12x squared. And when you know the rules of calculus, you'll be able to do that. So actually, in a lot of cases, there's no maths involved. You just write down the differential. The rules are that straightforward. So that's my new function. So now we've got a new function that tells us the differential, the rate of change, remember. So if I want to find the gradient of this curve here at any point, all I do is I take this function that we've just written down here, and I let x equal 1 or x equal 2 or x equal 3, any value I want, and I can find the gradient of the curve, the differential. But as has been pointed out, we're interested in the maximum value. So for maximum volume, the differential, which is dv by dx, equals 0. So I write that this 12x squared writing it in order of power, minus 128x plus 240 equals 0. So I've got to find x, okay? And that value of x will be the x that gives me the maximum volume. So as far as the manufacturing process is concerned, that's what I want to cut out of the corner of the sheet of metal if I want the volume to be a maximum. You might recognize this as a quadratic. And so in any quadratic equation, there's two solutions. So there's two possible solutions to this, two values of x that give a gradient of 0. And that's not surprising, because if we look at the original function, there's 2 points at which the gradient drops to 0. So it's going to give us both of these. We're only going to be interested in one of them. So we've got to solve this quadratic equation, and the formula might well be the way to go about doing it that we looked at last term. Before I do this, though, I can try and simplify it a bit, because I can look for a number that goes into all of these three things to try and reduce the numbers a bit, make it a bit more manageable. 4 goes into 12, and it goes into 128, and it goes into 240. So I could divide both sides by 4, because nothing divided by 4 is still 0. 12 doesn't go into 128. 10, 12 is 120, yeah. So 8 might, but we'll see. No, 8 won't go into there, will it? So no. So divide by 4. 4's into 12 goes 3. 4's into 128 goes 12. And 4's into 240 goes 20. Is that right? Is it 32? Oh yeah, thank you. Well spotted. And what's this one then? 40. Yeah, well, I don't know what I was thinking of. So that's a useful trick. Okay, if you've got a quadratic to solve, look for a common factor, because that just makes the maths a bit easier. The answer's the same, it just makes the working a little bit more straightforward. So now we use the quadratic formula to find x. X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay? Where a is the coefficient of x squared, so a is 3. B is the coefficient of x, so b is minus 32, and c is 60. So all I have to do is plug those numbers into that formula. So when I use this, to make sure I don't make any mistakes with the negative signs, I just rewrite the formula and literally just put each of the numbers in a bracket, because I can then see I've got a double negative there, so that's going to make that 32, positive 32 at the beginning here. Whenever I square a number, I'm always going to get a positive answer. So be careful of this bit, because if I put minus 32 into a calculator and square it, it gives a negative answer for some weird reason. So watch for that. Okay? It's always positive when you square a number by definition. So then I can simplify it before I put it into the calculator as far as I can. 32 plus or minus the square root of 32 squared minus 12 times 60, just to make it a bit easier for myself, all over 6. And then I get the calculator out, bang the numbers in. First time I put it into the calculator, this becomes a positive sign. And then what I do is I hold this information in the calculator and just scroll back and change the plus to a minus, and that gives me the other result. So use the fraction button on the calculator and then put this on the top and that on the bottom. Yeah, multiplied by. Yeah. So just try it and see what you get on your calculator. We have two solutions then. X equals 8.24 or 2.43. If we think back to the original problem, which was this, and look at this piece of metal, x cannot possibly be 8.24 because if you look at it, the width is only 12, so the maximum value x can have is 6. And then you're at the halfway point, aren't you, on that piece of metal? So if we look at the graph, where does it cut? At 6, because that's halfway. So the value of 8.24 is actually giving us the minimum value for the function, which we're not interested in. So we're only interested in this value, which is the real one for the volume of this box. So the answer we're after in this function is 8.24. Sorry, 2.43, yeah. Ignore this. And as far as engineering is concerned, as far as an engineer is concerned, that's something you have to do. When you're applying mathematics to a problem, is this, which of the results, as you often end up with quadratics actually, or more than one possible answer, you often have to apply it or relate it back to the real world and ask yourself, does this result make sense in the real world? Have I made a mistake? Or if I've got more than one answer, which is the one I'm interested in? And in this case, it's this one. Okay? So the value of x that's going to give me the maximum volume is 2.43. So I can now calculate the maximum volume. As a final exercise, volume equals, remember, 20 minus 2x, 12 minus 2x times x. Calculate the volume for x equals 3. Sorry, x equals 2.43. So if we put a value of x equal to 2.43 in there, we could find the maximum volume of the box. And it will come out to be hopefully something around about 260 odd, which is what we got from the graph.